Okay, so let me start with two administrative comments. I mean, first of all, remember that we have a tutorial, and the tutorial is it's a good thing to take part in it because it'll just go over ideas that were brought up in class, and this is Monday at 9:30. So we are tutorial group, I think number 8 or something, and it's dedicated to this section, so you should go to that tutorial. The other thing is that the Learn website is now on, so you can check on Learn for announcements of the course, and I will soon also activate the Piazza for this section of the course. Okay, so let me remind you what we were doing last time. So last time, I motivated the idea that we need a formal language. And in order to develop a formal language, we said that the language consists of two parts, syntax and semantics. Syntax is what the language looks like. The semantics is what the language means. And we start with the syntax. So we start with the kind of a little bit more boring part, but it's very important if you want to be able to do formal proofs. So we start with the syntax, and we want to build a language. So we want to create a set of all legitimate words, legal words of this language. And for that, we need to define an infinite set. And we said that we need a new tool for defining infinite sets. So the new tool, so we're talking about a tool for precise definition of infinite sets. And that's what we want to discuss now. And the tool was what I called inductive definitions. And the inductive definition consists of three components. So we have a set X, which is our domain set. And this is the set of elements within which everything is going to be defined. So for example, if I want to define the set of all even numbers, my domain set can be the set of all natural numbers or the set of all real numbers. If I want to define the set of all my relatives, then the domain set could be the set of all human beings. Then inside this domain set, we have a set A, which I call the core set. And this is the set of elements that I know for sure I want them to be in my set. And then we have a set P, which is a set of operations, finite set of operations. So what do I mean by operations? So this set P, we can think of it as a finite collection of functions. So P could be a set of functions f1, f2, up to some fk. It is finite. Each of those f's, so those f's could be, say, if I want to define the set of all even numbers, I could start with the number 0 and have the operation add 2. If each time I add 2, I am staying within the set of even numbers. So this could be one function. Or if I want to define the set of all my relatives, then I could have a function that takes you from a person to the children of this person. Okay, but those functions not necessarily have to be of one variable. They could be of more than one variable. So each fi, for every I, fi is a function from x times x. This could be some finite number ri to x. So what do I mean by that? The function could have more than one input. For example, I may want my function to be the addition of two numbers. So this function takes two numbers as its input, not just one number. So I have those functions that take elements of x and spit out another element of x. Like the function plus that takes 3 and 5 and spits out 8. Okay? And this could be even more variables in my function. So we have those three components. We have a domain set, we have a core set, and we have a finite set of operations. And now I want to define, what we wanted to define is the set IAP. We wanted to define the minimal set subset of X that contains A and is closed under the operations in P. So for example, the set of my relatives will be the minimal set of human beings that contains myself and enclosed under the operations son of, daughter of, husband of, and so on. The set of all even numbers will be the minimal set of numbers that contains 0 and is closed under the operation +2. Each time you add +2, if you were before inside the set of even numbers, you're still an even number. Okay, so this is where we finished last time. We wanted this definition. And now there was the question, is there any questions so far? I think the only point here that may not be clear is what I mean by closed under the operations. So let me just repeat it, just remind you. Reminder. I say that a set B is closed under the operations of P if for every, say, B1, B2 inside B, and every Fi in my set of operations, f of B1, B2 is also in B. So for example, the set of even numbers is closed under the operation plus. Right? The set of even numbers, if B, or let me write, not use the bottom part because it's difficult to read. Say, for example, if B is the set of even numbers, and P has only one function in it, and it's the function that takes f of x, y, and outputs x plus y. So I have here only one function in my set P. Then B is closed under P. For every x and y which are even numbers, and every operation in P, which the only one that I have is plus, if I take two even numbers and add them, I'll end up with a number which is also even. Right? And the set of odd numbers is not closed under the same operations. Okay, so this is where we were last time. And now, any questions so far? Okay, so now we want to show that such a set really exists. You know, all we are really concerned about having a precise way of defining sets. We want to make sure that if we define such a set, it really exists. The smallest set that is closed under the operation and contains the elements of A that I wanted to be there. Okay? So why does such a set exist? And to discuss this, we need to have some background in the notation of set theory. So let me just do a small digression to some set theory, just a reminder. So first of all, we all remember what is, so some background in set notation. Oh. Oh. At least it's not an electricity breakdown. Okay, so some background in set notation. So I guess we all know what is the union of two sets, right? It's a set of all elements that belong to either A or B. And we all know what is the intersection of two sets. It's a set of all elements that belong both to A and to B. But now we want to extend it. We want to extend those definitions to not just operation over two sets, but operation over any collection of sets. So let W be a collection of sets. And I want to define similar operations for collections of sets. So I want to define the intersection of W. So W now is a collection of sets. So how do I define the intersection of W? The intersection of W is defined as the set of all x's such that for every set B in W, x is a member of B. So I have a collection of sets. The intersection of this collection is all the elements that belong to every member of this collection. So for example, if we take an example, say my set W, now it's going to be a collection of sets. So say I have here elements, sets A, and I have the sets A, B, C, and I have the set A, C. So I have three sets in W. So what is going to be the intersection of W? What is going to be the set of all elements that belong to every member of W? Yes?
The set containing A?
The set containing A, because the only thing that is in the intersection of all of that belongs to each of those three sets is A. So the intersection of W will just going to be A. Does it make sense? Okay, let me consider a slightly more interesting example. So I have here three sets. The only elements that belong to all three sets is the element A. So here is a more interesting example. So say W is the set of all intervals of the form minus R plus R, such that R is a real number, such that R is a positive real number. So what do I have here? I have here the real line. Here is 0. Here is some minus R plus R. This is one of my sets. And I have all such sets in W. All the sets of the form plus R minus R, and the round brackets mean that the endpoints do not belong to the set. So each such interval are all the elements that are bigger than minus R and are smaller than R. So what is going to be the intersection of W? What is going to survive being in all of those sets? Yes? Just 0, right. So the only element that will survive that belongs to all of these sets is 0. Because every number that is not 0, if I pick any number here, x, there is going to be some R that will cut it out. So if I just want those numbers that belong to all of the sets, the only one that survives is the number 0. Now, does it make sense? Any questions here? So what will happen if instead I take W to be the set of all intervals 0R, such that R is bigger than 0? What will happen now? So now, instead of taking intervals like this, I take intervals that start here and take the intersection of all of them. What is going to be the intersection of W now? Yes?
The empty set?
Right, nothing will survive. The intersection is going to be the empty set because no number belongs, if I just look at intervals that start at 0 but don't take 0 and end somewhere, and I ask myself which number belongs to all of them. So no number belongs to all of them because for every number I can take a close enough interval that will leave it outside. So nothing will remain in the intersection of W. Okay? And similarly, so I have this operation of intersection over a collection of sets, not just over two sets. And similarly, I can talk about the union of such a collection W So similarly, I can talk about the union of a collection of sets W. And this is going to be the intersection of the set of all x's such that x belongs to every b in W. And the union of all W is going to be the set of all x's such that there exists some b in W to which x belongs. So I take all of the sets together and pour them all into one big bucket. So what, for example, what will be here? If I take this W, what will be the union of W? If I take all the numbers that belong to at least one of those sets. Yes?
All the real numbers?
All the real numbers. It will be the set of all real numbers. Every number will be there. Because for every number, there exists a big enough interval that will pick it into the set. So we can extend the operations of intersection and union to apply to a set of sets. Now, the only one thing I want you to note, which is interesting, is that for every, so this is just a simple claim. And the first part, it says that for every collection W and every set B, which is a member of this collection, I have the following two properties. The first property is that B is a subset of the intersection of W. You lost your chance to get a free point. B is a superset of the intersection of W. And the second property is that B is a subset of the union of W. Okay, so let us just, this is just a sanity check. Those claims are very easy, but they are a good exercise to see that we understand the notation. So there's some notation to understand it. What is the intersection and what is the, yes, what's, yes?
Union of W.
Oh, yeah. That's, yeah, it's a good question. It's kind of a typo. Okay. Someone last time that got a point didn't send me an email. You forgot to send me. So it doesn't expire, but you, my memory will expire. So. Okay, so let me just prove this claim. So what does it mean that the intersection of W is a subset of B? I'll just prove A. Right? So proof, I want to show that the intersection of W is a subset of B for every B that belongs to W. So what I need to show is that if I have an element here, every element that lives here also lives here. So you want to show that if I pick any x in the intersection of W, and we have to show that this x belongs to B for an arbitrary B in W, right? But that is kind of straightforward. So since x belongs to the intersection of W, for every B in W, x belongs to B, because that was our definition of the intersection of W. So in particular, it belongs to the B that I have there. Right? So I showed you that every x that is here is also here, so I have this inclusion. Just by the definition of the intersection. And the second claim is just as simple. Okay, so in some sense, the intersection is contained, is a subset of every element of those that are intersected. Okay. This is all the background that we need, and we can go back to our definition of sets IAP, and then, bear with me, we'll get to the logic. So, back to IAP, back to the new tool for defining sets. So recall, we have some domain X, we have some core set A, we have some set of operations P, and we want to show that there exists a set that contains A and is closed under the operation in P and is the minimal such set. So we say for IAP, let IAP be the intersection of this collection, the intersection of the set of all B's such that A is a subset of B and B is closed under P. So now I want to show you that such a minimal set exists. I gave you a definition of this set, and I want to show that it really meets all the requirements. So now I want to show you a list of claims. What do I want to show? So I want to show the following thing. Is that, first of all, property 1 is that A is a subset of this intersection. So let's call this set W of A and P. Right? So A is a subset of this intersection of the set W of AP. The second thing I want to show you is that this intersection of WAP is closed under P. And the third thing I want to show you is this is the minimal such set. Because as the definition, we said we want the minimal set that contains A and is closed under P. So I want to show you this is minimal. So intersection WAP is the minimal set satisfying requirements 1 and 2. And as a conclusion to being minimal, I want to show that there is no other such set satisfying 1 2, and 3. Okay? So we have a new tool for defining sets. We want to show that it's a good tool of defining sets. So I want to show you that such an object always exists. And I am pointing to a specific such object, which is the intersection of all of those sets. And now the proof is very straightforward. Just make sure that the claim makes sense to you. Right? I want to show that this minimal set exists, and I point to what it should be. It should be this intersection. And now we are going to prove those requirements one by one. All of them are completely trivial. Why is A subset of this intersection? So to show that A is a subset of this intersection, I want to show you that if I have an element of A, it is an intersection. Yes?
It's because A is element of B, and it shows in the definition of that?
Right. Because the intersection are things that belongs to all the B's in my set. And every B in my set contains A. So if I pick an element of A, it is in every B in my set. Because I only took their sets that contained A. So this is because every B that sits here contains A. So element of A belongs to all of them, so it belongs to the intersection. What about closure under the operation in P? So for closure under the operations in P, for 2, so assume that I have some B1, B2, it doesn't matter, and I pick some. So pick some B1, B2 in this intersection of W, and pick some F in P. I want to show you that F of B1, B2 belongs to this intersection of W. Why is that the case? Because if B1 and B2 belong to the intersection, then they belong to every B in a collection. And every B is closed under the operations. So if they belong to the intersection, so if we pick any B in my collection, in this W of AP, I pick any such B, B1, B2 will be in B. And B is closed. Because in my collection, I only considered sets which are closed under the operations. So F of B1, B2 belongs to this B. And this applies to every B. So F of B1, B2 belongs to the intersection of all of them. So I know it almost feels like I'm saying nothing, like I'm repeating myself the same sentence but there is something to observe and prove here, right? If I want to show that the intersection is closed under the operations, I want to pick 2 elements there, or 3, or whatever the F requires. I pick these elements. I say, since they are in the intersection, they belong to every B there. Since every B is closed, then F of those elements will be in every B. But if F is in every B, it means that it is in the intersection. So I showed you that if I pick any elements in the intersection and apply any F, I will stay inside the intersection. So the intersection is closed. Is there a question? No, but it's good. I mean, if something is unclear, I can assure you that other people will also be happy to hear an explanation. Nothing. Okay. Okay, so we resolved 2. Now I want to claim that this is the minimal set that satisfies those 2 requirements. So what do I mean by a minimal set? By minimal set, so for property 3, we have to define what do we mean by minimal set. So what I'm saying is that let, say, pick any letters that you want. Say D. Be any set satisfying properties 1 and 2. I claim that then this intersection of W is a subset of D. So that's what I mean by minimal. It is smaller than any other set that satisfies property 1 and 2. Can anybody see the proof of this? Why is it the case that if I pick any set that satisfies, includes A and closes under the properties P, then inevitably this set will be a superset of this intersection? Yes?
Suppose you remove an element from the intersection and it still works, still satisfies.
You are going too complicated. It's simpler than that. Yes?
Can you do a proof by calculation?
We don't even need that. Yes?
Just say that set D contains this set, because any element in this set is in the other set, because any element in this set is a composition of bases.
You're still getting too complicated. It's really, really straightforward. Yes?
If D satisfies 1 and 2, then D must be an element of W.
Right. If D satisfies 1 and 2, then D is one of those B's. Because here we took the set of all B's that satisfy 1 and 2. So if D satisfies 1 and 2, D is an element of W. And we said that if I pick an element of W and take the intersection of W, then the intersection of W is smaller. That was my simple claim just before. Right? Since in this case, D is an element of W. And if I take the intersection of W, I am contained in every element of W. Right? If I take an intersection of two sets, if my W is two sets, then the intersection of W is A intersection B. It's a subset of A, and it's a subset of B. Or if you want it pictorially, we have all those B's that we intersected in W. W is the intersection of all of them. So if I pick any such D, D is one of the sets that I intersected. So it is a superset of the intersection. Okay, so W is this collection of sets. The shaded area is the intersection of W. And D is one of the sets in my collection, because I took in my collection all the sets that satisfy requirement 1 and requirement 2. So therefore, the intersection of W is really the minimal such set. Okay, so let me erase the picture and just leave the claim. And my last claim is that I'm saying that such a set is unique. There is only one set that satisfies the requirements 1, 2, and 3. Why is there only one set that satisfies 1, 2, and 3? Yes?
If there was another minimal one,
Right.
It would be a B that would be in the intersection and therefore would make that intersection smaller.
That's one way of looking at it. We can even do it simpler. We can even do it more simply than that. Yes?
If it's smaller, then it's the minimal set. If it's the same size, then it's the same set.
Kind of. So what I'm saying is that if I have two sets that both of them are minimal, say I have two sets, call them, I don't know which letter I haven't used yet, E1, E2, both of them claim to be the minimal sets that satisfy property 1 and 2. So since E1 is minimal, E1 is a subset of E2. Because E2 satisfies property 1 and 2, and E1 is the minimal such set, so E1 is a subset of E2. But E2 is also minimal, because we said minimality is unique. So E2 also claims I'm minimal. So E2 should be a subset of E1. And if I have two sets that each of them is a subset of the other, then they are the same set. So the requirement of minimality inevitably tells you there's only one such set. Because every minimal set is a subset of any other set with these properties. So the two minimal sets will be subsets of each other. Okay? So you see, once we just stick to our simple notation, we don't have to worry about the size of the sets, proof by contradiction. It's all just carefully looking at the notation and what it means. Okay, so that was a very abstract part. I mean, I do intend to, scare all of you. This is the enriched section. If it's too abstract for you, run away. But I can assure you this is one of the scariest parts of the course. The rest will not be as bad. I mean, it's not scary that in the sense that I'm writing horrible integrals on the board, but in the sense that it requires some kind of abstract thinking. Yes?
But like, doesn't your proof that you kind of did there assume total ordering though? Like,
No, that's what I mean by minimal. A minimal set is a set that contains in every other set in with the properties. The question is, what do we mean by minimal? I said that the set is minimal with properties 1, 2 if it is a subset of anybody else that satisfies 1, 2. So by being minimal, E1 is a subset of E2 because E2 satisfies 1 and 2. And by being minimal, E2 is a subset of E1. It's just the meaning of minimal. Yes?
But in some situations, it's not possible to have like a number of minimal sets satisfying some property.
What do you say?
That is, there's not supposed to be just one minimal set.
No, the question is, what do we mean by minimal? If you have some kind of ordering, there are some orderings in which you can have several minimal sets. But if my ordering is inclusion of sets, then I cannot have two sets that each of them is included in the other. It will be the same set. Okay? So what have we established? We established that this proof of IAP is a valid way, this definition is a valid way of defining sets. Such sets always exist, and they are uniquely defined. And that's important because this will be a tool that we will use over and over again. So if you got confused by the proof, we will go over parts of it in the tutorial, but also you can just forget about it and say, what is the bottom line that I have to remember? The bottom line that we have to remember is that this tool for defining set, this IAP tool, is a valid way of making definitions. Such an object always exists and is uniquely defined, which is very important. So let us now go back to logic. So now we have this new tool in our hands that allows us to define sets. We want to go back to logic, and we can start defining our first language, our first logical language that we are going to talk about. And this is, so defining the language of propositional calculus. So now we are coming to a formal definition of the first language that we will discuss. And at this point, I'm only defining the language, only the syntax. I'm not talking yet about meaning. Just what are the words of my language? So I'll start by a notion of symbols. So we have a set of, so we fix a set of symbols or characters, and they consist of two parts. The first part is consists of left bracket, right bracket, wedge, V, arrow, and right angle. So I will use all those symbols. Those are going to be characters that I'm going to be applying in the definition of my language. So we can think of those as the letters for writing my new language. And on top of them, I also have variables, which I'll call them, say, P1, P2, and so on, Pn. So those are also letters. And the distinction is those are called variables. And we can have many of them. We will usually use just lowercase letters for variables. And those are called logical symbols. And the difference is that when we will get to the meaning, those logical symbols will always have the same meaning. But the variables could have different meaning. I can say, when I write P or Q, so P can have, say, I can say either today is a weekend or I don't want to wake up. So this is one way of assigning meaning to each of them. And in different applications, we'll assign different meanings. But this will always mean or. So I say this is a logical symbol. P and Q will be different things. So these are the letters of my language. Now, the next step is, so I have the first set is a set of symbols or characters. Then from them, I build my domain set. So the next level is the set of what we call expressions. And expressions are just going to be any finite sequences of symbols. So expressions could be things like P or Q, but expression could also be things like left bracket, left bracket, left bracket, and. This is also an expression, because this is also a finite sequence of symbols. So expressions is a big set. It's well defined. It's all the finite sequences of symbols. And we have defined our set of symbols. So far, it's kind of very boring. Now we want to define our words. So the first element was the set of symbols. The second element was the set of expressions. And now I want to define the set of valid words. It's like you want to learn a new language, right? You want to learn, say, I don't know, if I think of language that I know, I want to learn Hebrew. So the first thing I want to learn is what are the characters of Hebrew. So I have things like this. Very strange symbols. Those are the characters of Hebrew. Now, expressions are every collection of characters. Some of them have no meaning. So I have to give you what is the dictionary. Which collections are a word in the language and has a meaning. So that's exactly what we are going to do now. So we want to define which of those expressions is a valid word. So we want to define, that's the most important part, the set of meaningful or legal propositions. There are the words of my new language. Sometimes we call them, you'll see in the book, they are sometimes called WFFs, which means it's not WTF, it's WFF. And it stands for well formulated formulas, something like this. Anyway, we will not use this WTF. We will use, we'll call them propositions or words. And now we are going to use our definition by inductive definitions. So we are going to define the set of words as an IAP. We are going to use this new tool to define them. So our set X, so in order to define IAP, I need to give you three components: the universe X, the core set, and the set of operations. So my universe X is going to be the set of expressions, all finite sequences of symbols. And we saw what the symbols are. Now the set A, the core set, is going to be the set consisting of all single variables. So it's a set consisting of P1, P2, Pn, all single variables. Every single variable will be a word in my language. And now I need to tell you what are the operations. So my set of operations contains 4 operations, and I will write an operation as I'll write it like this. If I have here alpha and beta, the operation, this is the input operation, and here is the output of the operation. So if I have a sequence of symbols alpha and a sequence of symbols beta, my first operation generates alpha or beta with brackets. And my second operation takes 2 sequences, alpha and beta, and generates alpha and beta with brackets. And my third operation takes alpha and beta and generates alpha arrows beta. And my last operations take an expression alpha and generates this expression. So these are my operations. So my set of propositions or words in my language, or propositions if you want, is I of this A and this P. The set of all expressions that I can generate by starting with the single variables and applying these operations. So now we are done with our definition, but let us start seeing what does it generate. So what does it generate? So for the first thing that I have, so here are examples of propositions that are going to be in my language. So first of all, there's going to be P1. Because how do I know that it's a word in my language? Yes?
It's in the core set.
It's in the core set, yes.
So in essence, symbols like for all and there exist are not.
They're not in this language. For all and there exist are not in this language. This is a very simple language. All we have are those and or arrow and not. So P is in my language. P1 is in my language. Also P17 is in my language. And P5 is in my language. All those guys are in my language. Now I can apply any operation. So I know that not P17 is a member of my language. And I know that P1 or P5 is a member of my language. And now, if those guys are members of my language, I can apply any operation to each of them and still remain in my language, because we know that IAP is closed under the operations. So now I can pick any operation and apply to anything that I know that's already there, and I'm guaranteed that the next thing I'll generate is also a legal word in my language. So not P17 is a legal word in my language. And not P17 or P1 or P5 is a legal member of my language. Each time I can take words that I already have in my language and apply any of my 4 operations. So the only point that might be a little unclear here is that the way I write the operations, I write the input at the top and the output at the bottom. Right? And the operations apply to any expression. So if I apply this operation to the expression not as my alpha and bracket as my beta, I will get not or bracket in brackets. I mean, I can get complete nonsense, but the operation is well defined. I can input any sequence, any expression, any other expression, apply this operation, get a new expression. It could be all of them meaningless. IAP is all the things that I can generate if I start from the variables and apply operations. So now I have a well-defined set of words in my language. As opposed to English, here I have a very clear definition of what is a word in my language. Yes?
Basically, P implies not P will be a word in your language.
Is P implies not P will be in a... Yeah, sure, but let's just check it. I mean, you see, if I follow the rules, the nice thing is that at this point, we don't have any meaning. So it's a very important point to notice. At this point, there is no meaning, semantics attached to words at this point. So for example, P1 and not P1 is a legal word in my language. And the word P1 or P2, is it the same as the word P2 or P1? Are they the same or not? They're not the same because there's no meaning. If there's no meaning, all I can check is that symbol by symbol, are they the same or not? So they start the same. Oh, this is P1, this is P2, they're not the same. So they're completely different because there's no meaning. It is just collections of symbols. It's just a game of symbols. So now we need a way of showing that something is in the language, distinguishing what is in the language is not and not in the language. Okay, so let us see, how can I prove, if you give me something, you claim it's in the language, how can I prove it's in the language? And notice that this is very similar to the way we define programming languages. If you want to define a programming languages, you have some kind of set of basic symbols that are going to be in your language, and you have operations. And then you can apply the operations to elements that you already have. If this is a program and this is a program, then you can write from this a new program that will say while something, do something, or I don't know what your language is. So it's the same thing here. And now we want to do the job of a compiler. I give you a sequence and I ask you, is it a legal program? Is it a legal word? How can you check it? So let us try and see how we do it. So I give you, how can we show that something is a legal word in my language? So say I give you this word, which is, I will not just restrict myself to P1, P7, and so on. Every lowercase letter will be considered a variable in my language. So what about, I want to show you that, say, P or Q arrows, not P and Q, all of this not. I want to show you that this is a legal element. Is it?
No.
It's not. I know I need all kind of new brackets, right? Yeah, I need another bracket here. So let us check, how do I know that, can I show that something is in my language? So the way to show is, I mean, what do we know? We know that the atoms are in the language, and the language is closed under operations. So in order to show you that something belongs to the language, I have to show you how can you get there by just starting from the atoms and following the rules. So I can say, OK, P is an atom. It's a legal element to be there. Q is an atom. Is allowed to be there. And therefore, I can apply operation, the first operation, and get P or Q. So I know that this guy is in the language. Similarly, I can continue here and say, oh, P is in the language. I also know that Q is in the language, so therefore P and Q is in the language. Now I can apply another operation and say, therefore, not P and Q is in the language. So I already know that this guy is in the language and this guy is in the language. So now I can apply the operation arrow and say, therefore, this guy is in the language. P or Q, arrows not P and Q. How many brackets I need? Something like this. So now I know already that this guy is in the language. And now I can go one more step and say, OK, now I apply the operation negation and get that not of all of this in the language. And I showed you that this is in the language. So I somehow generated a certificate. It is like that. Assume that I'm having a party. And I invite my friends, and I tell my friends, you know what, I really worry that there won't be enough people in my party. So if there's someone that you know and you want them to join, you are allowed to invite them. Now some guy knocks on my door and says, I want to join your party. And I ask, are you a legal participant in my party? So he should generate such a sequence. You know, Jeff is your friend, sure. And Julie is your friend, sure. And I am a friend of Jeff and Julie. Oh, no, a friend of Jeff and Julie is this guy. And his friend is that guy. And his friend is that guy. And he gives me a long list like this that ends up in himself. And I have a certificate that he is allowed to join my party. OK, so such a sequence is the way that we prove that members belong to our IAP set. And as silly as it looks, it's a very important object. And we will see it again and again in the course. So let us give it a name. So this is called a construction sequence for an expression alpha is a finite sequence alpha 1, alpha 2, alpha n, such that what do I require? Each alpha I is either a member of the core set A, or it is the result of applying some f in P to previous, to say alpha j, alpha k, where j and k are smaller than I. So this is a cumbersome formal way of saying what we saw before. So what is the construction sequence for alpha? And of course, alpha n should be equal alpha. So the construction sequence is kind of the certificate that you belong. So it's a sequence that starts from elements of the core set. And whenever you take a new step, you have to say, I was generated by elements that you already approved that belong to your set. So this here is a construction sequence, because every element here either belongs to the core set, or it was generated by things that I already saw before by one of my 4 operations. So this is my notion of a valid certificate. Why is it an interesting object? Because if we think forward for the course, look at what is a proof. A proof is also a sequence like this. If I want to prove something formally in mathematics, then I have a sequence of arguments such that each of them is either, say, an axiom, or it follows from previous arguments by some well-known combination of arguments that I know that works. So a proof has this nature. A proof is kind of an argument which is a sequence of claims. Each claim is either a core claim that I know that it's true, or I can show you why this new claim follows from things that I've already showed you. So we will have this type of construction sequences occurring over and over in the course. The structure IAP will occur a lot, and when we have a structure IAP and I want to show that a member belongs to it, I can come up with a construction sequence. Now there is a theorem here that I'm not showing you because it's going to become too technical and boring, but you will do it as an assignment. And the claim is that this is really a valid way of checking membership. So for every x a p and a and expression alpha belongs to IAP if and only if there exists a construction sequence for alpha. So if you really belong, you can come up with this sequence that proves that you belong. And if you can come up with such a sequence, you really belong to IAP. Okay, what?
So unless it's in A, right? Like if it's a member of A, then is there necessarily a construction?
The construction sequence would just be it.
If alpha is in A, then the construction sequence can be just alpha. Just one step. If you're in A, you don't need a sequence. You just need one step. Say, me, here I am. Okay? Yes?
Why do expressions have to be finite?
Oh, that's because, I mean, there are languages over infinite expressions, but that's becoming way beyond what we'll do in this course. So we only talk about languages in which words are finite. I mean, it's very difficult to express yourself in a language in which words are infinite. The listener needs a lot of patience. Okay, so we have some, we will go back to it and practice it. So we have some kind of a tool that can show us that something is in the language. But now comes an interesting question. How do I show to you that something is not in the language? This is more challenging. I want to show you, for example, that this expression P bracket arrow is not a proposition. This is an expression. It's a sequence of symbols. I claim that it's not a proposition. We all kind of agree that it's not a proposition, right? But how do I show you that it's not a proposition? Yes?
You can make two rules.
Okay, so what are you trying to do? You're trying to tell me, I mean, and that's what we are going to do. In order to show that someone is not a member, it's more difficult because to show you that something is a member, all I need to do is give you a construction sequence. Here is how it was constructed. Why do I belong to the family of, I don't know what, Queen Elizabeth? Because I'm the nephew of the husband of the da-da-da-dam that goes back to Queen Elizabeth. Okay, but how do I prove to you that you are not as royal as I am? Now it's harder. I have to show to you that no matter which way you go, you will never reach the Queen Elizabeth, right? So how do we show such more difficult things? So what you suggested is a good way to go. What we are going to do is, so the questions I want to address is, what tools do we have for showing that something is not in the family? So the tools that we are going to address is, think of this is my set of all possible elements. And here is my core set A. And here I start applying operations. And I get to something which is my set IAP. Right? So I start with my core set A, and I apply operations and get new elements, and apply operations to them and get new elements, and so on and so forth. And then I get this IAP, which is the minimal set that is closed under the operations. And now you come to me with this cute, strange guy, this P, blah, blah, blah. And I want to tell you it's not inside the set. So the way I'm going to do it is I'm going to find some property such that I could show you that every member of my set has this property, but your candidate does not have this property. So the way we're going to show that something is not in the set is always by coming up with some property that we can show that holds for every member of the set, but does not hold here. So let me show you such a property that rules out this guy. This is going to be easy. So coming up with a property, it's not so difficult. Proving that this property holds for all members of my IAP is a little bit more difficult. So what property can you think of that this guy doesn't satisfy and every member? Yes?
Matching brackets.
Matching brackets. OK, that's a complicated property, but it's a correct one. So one such property, let's call it property 1, is that in every proposition, the number of left brackets equals the number of right brackets. Yes?
Can I recommend another property?
What do you say? You have another property?
Yeah.
OK.
If the variable is not just a atomic variable and does not contain a left bracket at the start, then it's not in.
Right. So this guy violates lots of properties. And your property is also good. The property that he suggests is that every legal word is either a single variable or it starts with a left bracket. That's also a good property, right, that this guy violates. So whenever we want to show that something is not in a language, we want to find a property that is satisfied by all members of my set and is not satisfied by this guy. But now, how do I show it? So now we want to ask this following question. So how do I show, how can we show that some property T is satisfied by all members of IAP. Right? So let me give you another, since it's the last 10 minutes of the class, let me give you another, a little bit entertaining example of this. So, I mean, usually when I prepare this class, I use cups, but I don't have here enough empty cups, only one. So I'll draw the cups on the board. So assume that I have 3 cups here, and the 3 cups are like this. So I have 3 cups, one of them is flipped, 2 of them are upright. Now I am allowed each time to flip 2 cups. So each time I'm allowed to flip 2 cups. So I can take this and do flip this guy, get to this situation. Can I get to all cups are upright? So each time I'm just allowed to flip 2 cups. Can I start with this and have all my cups upright? What do you think?
No, because each time you're preserving the parity of the
Okay, right. You're a bit too smart for me, but for what I wanted, but that's good. So what I'm saying is, first of all, note that we have here a case of IAP. The set of all legal configurations of the cups is IAP. What is my A? What is my core set that I started with? The first orientation. And what is my set P of operations? Flip 2 cups. So here I have my A is thus the original configuration. And my set P has 3 operations. Operation 1, F1, is flip rightmost 2 cups. Operation F2 is flip the 2 end cups. And operation F3 is flip leftmost 2 cups. Right? So I have 3 operations, and IAP is the set of all configurations of the cups that I can reach. So it's exactly the same situation that we had with propositions. I have, what is my set of expressions here? What is my X here? What is my universe? My universe consists of all ways of putting together 3 cups. It's not so big. That's my universe. And in my universe, I have here in this core set only 1 configuration. And I have operations. And I want to show you that this configuration is outside the IAP. So I want to show you some property that holds for all of them and does not hold for this guy. So how do we do it? So first of all, we have to find a good property. And here already suggested a good property. So to show that I cannot reach all cups upright, we use the property T is the number of upright cups is even. That's my property. So now in order to show you that it holds for any legal configuration, I actually want to show you 2 things. First of all, I want to show is that every member of A has property T. And secondly, I want to show you that if some configuration, some alpha 1, alpha 2, alpha 1, alpha 2 has property T, and f is one of my operations, then f of alpha 1, alpha 2 has T. So I want to show you that when I start, I have the property, and whenever I take a step, I still have the property. Therefore, I showed you, why will it show that all elements of IAP have this property? Why, if I show you these two things, I show you that all elements of IAP have the property? Can you give me a formal argument why showing these two requirements implies, if I have these two requirements, let's write it like this. If I have these two requirements, then every member of IAP has property T. I can write it like this. So why can I make this conclusion? Yes?
It's an induction argument on the number of operations.
Ooh, you're going to. We are doing things completely simple. Everything is inside this class. You need nothing outside what we show today. Yes?
We saw earlier that any valid expression has a construction sequence. So.
Too complicated. Yes.
Because it's closed under the operation.
Right. I showed you that. What does it show? It showed that T contains A, and T is closed under the operations. Right? T contains A and closed under the operations. So T is one of the B's that are intersected. You remember IAB was the intersection of my W, or the intersection of all B's such that B is a superset of A and B is closed. And we said that every such B is a superset of the intersection of W. Right? And this is exactly what I'm showing you for T. I'm showing you that T contains A. It has property 1. Every element of A satisfies T. And T is closed under operations. If alpha and 1, alpha 2 satisfy T, then applying F still satisfies T. So I show you that T is one of the B's which are intersected here. And we showed that the intersection is a subset of everything that is intersected. So IAP is a subset of T. So we don't need any claim for induction, going by steps, induction on the number of steps. It just follows directly from the very simple property that when I intersect a collection of sets, the outcome is a subset of everything in intersection. So all I have to show you is that T has those two properties, 1 and 2. OK. Yes?
But isn't F a unary operation? So why does it have?
Oh, yeah. I just, in the case of cups, F was a unary operation. It could be unary, binary, triple, whatever. Right. In the case of the cup, it was a unary operation. So let me just show you how you can make a fortune. I told you at the beginning of the course that you cannot get rich from logic. But here is an example of someone that did get rich from logic. So what he did, I just have the 2 minutes that I need to show you how to get rich from logic. I mean, it's a real story, true story of someone who got rich from logic. So what he did is he distributed this type of square. You probably know it. You have this kind of a square, and you have here an empty box. And here you have numbers. These are squares, and the squares can be moved around. 1, 2, 3, 4, and so on. 5, 6, 7, 8, and so on. And the only thing that you do is you put here 15, and you put here 14. So you know this game, that you can slide the small squares around. So he was distributing this kind of slightly converted square, and was selling them for $1 and promised $1 million to anybody who will show them how to arrange them in the correct order. And people were buying it because they were thinking, I mean, OK, I'll try a little bit. I can get $1 million. But what this guy had is in back pocket is a proof that this is an IAP. You see, this is my set A. This is the initial configuration. My operation P is just slide any of the adjacent squares into the empty box. And you can show that the correct configuration is not a member of IAP. So once you have such a proof, you're guaranteed that nobody will claim your $1 million. So go to the world and tell me on Tuesday how much you managed.